That's my standard answer to how do I practically apply potential field algorithm. But then some people will not leave me there. Some people will ask me another question. But that's all a toy problem. Cheap robots, cheap cameras, static scenario. That's not my problem. I have a big robot. How do I do it with that? So let's take that example as well. That's your map. That's your goal. You always know the coordinates of the goal. Believe me, you always know the coordinates of the goal. Goal are coordinates. Now, for some time, I'm going to make you believe that you know the position of the robot as well. So, finding Q, so finding position of robot is called the problem of localization. And I've taken a separate series of lectures how to solve that problem as another elective. The easiest that I can tell you is what many people playing with small robots do. So every wheel has what is called as encoder, so it has spikes like this, and there's a transmitter receiver here. As the wheel turns, you get pulses over here, so you know how much the left wheel has turned, you know how much the right wheel has turned. Starting, you know the position of every robot. Every robot starts from the charger, so you know your current location, you know the robot started its journey from the charger, you know how much the left wheel has turned, how much the right wheel has turned, so you know your position approximately. So if you know where the goal is, you know where the robot is, so you know the attraction between the goal and the robot. So you can calculate F attraction. Assuming that the problem of localization has already been solved, but actually it hasn't. So this can be calculated. This is known and this is known. The problem is with repulsion. Repulsion is always the problem. So previously we used bushfire algorithm, overhead map. Now the problem is the overhead map is A, not given, and B, even if overhead map is given using a technique called as mapping, the problem is they are moving people. The overhead map will not have those moving people, and those are legitimate obstacles. So now what I'm going to do is I'm going to make use of an expensive sensor called as a LiDAR. Just costs in a 2D LiDAR over a lakh, a lot of money. So it sends a laser beam. The laser beam strikes the object and the laser beam comes back and it calculates the distance. The laser beam is extremely accurate, it doesn't diffract, and the diffraction which is actually used to measure the distance is extremely accurate, it has millimeter accuracy. The only thing is that this laser beam turns around. So that's my laser beam. It strikes, it turns around. That's my another laser beam. It strikes, it turns around. And let's say this was my obstacle, this was my direction. So I've got all these laser beam that strike, that turn around, strike and turn around, strike and turn around. So let's say that this laser beam was at the direction of alpha from the direction of the robot. Okay, let me take an example where the orientation of the robot is positive. Here the orientation is negative. So let me correct the example. So theta is the orientation of the robot. And with respect to the robot, this is what is my laser ray. That is at a direction of alpha, and it strikes this, and I know this d alpha, which is the distance reported by a laser ray at an angle of alpha. The laser ray will go all 360 degrees. The back of it is not useful because it will detect the robot itself, so that's completely useless for me. So I'll say F repulsion from a laser ray at an angle of alpha is equal to, oops, okay, so it's half give repel, oops, not half, it's force, it's not, d alpha. So distance is known, which is d alpha. And what I'll do is, I mean, the distances are measured from the circumference of the robot. So I'll subtract the radius of the robot. And the angle of this thing will be at a direction of theta plus alpha. So at the theta plus alpha is where this laser ray strikes. So if I need to apply a force, I need to apply it in a negative direction of theta plus alpha. So that's cos theta plus alpha and sine theta plus alpha. And in its negative direction is where I'll apply the force. So, easy enough. That's what happens. Now, so far so good. Now the problem is sometimes people ask me, I don't have so much of money to buy a LiDAR. It's a very expensive sensor. What do I do? So, an answer to them as well. So, you buy in a ring of sonar sensors. That's very cheap. Everybody can afford it. You get rings of 8 sonar sensors. You get rings of 4 sonar sensors, you get rings of 16 sonar sensors. Beyond that, the radius of the robot does not allow. So it sends rays at these directions. Usually they are not mounted at the back. I've shown it at the back, that's a different reason. So this reports one obstacle, this reports one obstacle, this reports one obstacle, and so on. And you take all those obstacles and apply exactly the same formula. Every sonar in the sonar ring is at an angle. Sonar is poor man's LiDAR. So if you cannot afford the sonar, if you cannot afford the LiDAR, you take a sonar. Extremely bad sensor, but then extremely low cost as well. Now here an interesting thing happens. So suppose, and this is what's called as a black spot. So let me denote it by black. It's the same definition that you would have seen in movies where people discuss, this camera looks here, this camera looks here, but this region no camera looks. It's the same definition that you would have heard in examinations. This invigilator is looking here, this invigilator is looking here, here nobody is looking, so you can do anything over there, it doesn't matter. So, sonars will have too many black spots, nobody is looking at there. So if there's an obstacle over here, it doesn't mean it will collide because attraction, repulsion, so it will take a little bit turn around over here, and only when it comes here, the front sonar will actually look at this obstacle and take a corrective action. But the black spots, they cause too much of a trouble. And the only way out is to increase the resolution. There are other those things that when you look at an obstacle, register it in your knowledge base, in your memory, but that usually doesn't work when your robot is extremely cheap and your location, the skew is also extremely noisy. So the only practical way out is to increase the resolution by more expensive sensors. But then, namesake, I can say that when you look at an obstacle, just register its coordinates in your brain. So even if you're not looking at an obstacle, you know its coordinates from the brain. That's your model, and that's your model-based decision making. And that is exactly how I would actually end up in making all these wonderful robots navigating using the potential field algorithm. So attraction, the localization is assumed to be known, the goal coordinates are assumed to be known, and the attraction is directly calculated. The repulsion, we use all these proximity sensors, real or virtual, and using that, the robots can avoid each other because the proximity sensor says at which direction is the obstacle, at what distance is the obstacle, and it applies a force in exactly the opposite direction. Now, it does change a little bit if you have a robot Q and another robot R, and both of them can communicate. So this tells its position to this one, this tells its position to this one. So you will have repulsion force as k rep by dq comma r, the whole cube, minus 2r, 1r subtracted for this, 1r subtracted for this. So this is dq comma r minus 2r. And this is the unit vector away in that direction. So this is the unit vector away from the direction. It can be calculated without sensing because both robots apparently knew their position and they communicated it to each other. And because they communicated it to each other, you can have a look at it. It doesn't mean if there are n robots, there will be n square interaction because every robot will communicate its position to a central master. The central master will calculate the interaction only between the k nearest neighbors, which is a logarithmic of n operation by the KD3 data structure, not discussed around over here. And the last part that I'll discuss is because of this wonderful course on manipulation that you've been through. So I say potential field for a manipulator. Now there are two ways by which it can be applied. So let's draw a manipulator. The first thing that you apply is you say that each one of these arms, it receives a repulsion force. So this will receive it because of this obstacle is closer, this is far away, this will receive because of this, that's far away, this is close. And all these are converted into torques. So these are the forces. Force can be converted into torque, and then you say the joint speed, the angular speed of every joint is proportional to the torque. Fair enough. The other way it's implied is you say I don't care about the body, all I care about is this center of mass. So you do all the forces on the center of mass, you don't care about this thing, you calculate the resultant repulsion force. That resultant repulsion force of the end effector, so the resultant force of the end effector is converted into the desired speed of the end effector. So this is the Cartesian speed of end effector, and that can be converted into the angular joint speed of the, and this is of course called as a Jacobian, or the manipulator Jacobian. So that's another way potential field is applied into the manipulators if you have an understanding of the manipulator. So technically what I've taught you is a nice arena and lots of static obstacles, dynamic agents. By the way, we don't look at static obstacles in the lab component as of now. It's a part of another course. So what I taught you is all the maps and lots of moving people, each person going somewhere or the other and it feeling repulsion and attraction. And this entire game of attractions and repulsions between everybody is, of course, what you know as life. I hate you, you hate me, we hate each other, we challenge each other. I know whom you love, not really. When I used to be in campus, I used to know whom you love. And we all make decisions using this hate, love, attraction, repulsion. We model exactly the same thing in this way, giving you ability to move multiple simulated agents around, avoiding each other reaching their respective goals, which ends the simulation as well.